So in the first part of the lectures on chapter 6, we discussed the derivation of the Euler Bernoulli beam, which is the beam model that's used in most of the applications of structural engineering. There's another beam that we're not going to cover in the course, which is another beam model called the Timoshenko beam under bending, which allows for shear deformations. And this is covered in more of a graduate course. Then we're going to discuss beams under axial loading, but we're going to delay this until the examples. So we're going to jump right away into examples. So in the first example, we would like to draw this. We would like to find the stresses and throughout a cantilever beam. So consider a cantilever Euler Bernoulli beam, so a beam that can utilize the Euler Bernoulli beam model for the analysis of the deformation and the stresses. It has Young's modulus of 20 gigapascal. The beam is 5 meters long and has a rectangular cross section. Meter long and has a rectangular cross section. The height of the beam is equal to 0.5 meters and the width of the beam is 0.25 meters. If a load of 125 kN is applied at the free end, draw the contour plot of sigma on 1. So we want to know what sigma on 1 is at every point, what sigma on 2 is at every point, and what the von Mises stress along the beam is. We also need to sketch the principal stress direction at the top fibers, the bottom fibers, the neutral axis at quarter of the height of the beam, at the support. So I'd like to know at this point what is the stress, which is actually made out of a matrix, and at this point what are the principal stresses and the principal stress directions. So in order to solve this beam, the first variable that I would like to know is y. And y is the vertical displacement of the beam. So if this is x1 and this is x2, I'm looking for the displacement function y. Where y is the displacement of the neutral axis. Displacement of the neutral axis. It's a function that is changes according to the location on the beam. So the differential equation of equilibrium in terms of y tells me that this y that you're looking for is a function of the distributed load on the beam, but q is equal to 0. And the problem tells me that you have boundary conditions of the beam. The boundary conditions are, I'm going to draw the center line of the beam. This is 125. The boundary conditions are, right here the displacement is 0, right here the rotation is 0, right here I don't know the displacement, I don't know the rotation, but I know that the shear, which if you remember the positive directions where this is positive shear, this is positive shear, positive moment, So at this end of the beam, this is positive shear of 125, and the applied moment at this point is 0. Here the shear is equal to the reaction, which is unknown. The moment is equal to the unknown moment, which is the moment is equal to the unknown reaction, which I don't know. So I have 4 boundary conditions: 0, 0, 125, and 0. Knowing the boundary conditions and the differential equation, I can proceed with solving it. EI y will be equal to a constant multiplied by cx1 power 4 divided by, power 3 divided by 6 plus c2 by 2 plus c4. And I've found this by integrating this original differential equation. In the process of integration, I pass through the rotation, which is equal to c1x1 squared over 2 plus c1x1 plus c3, and this is equal to ei dy by dx. And ei d2y by dx1 squared, which is equal to the moment, is in fact equal to c1x1 plus c2, and the shear is equal to ei d3y by dx1 cubed is equal to c1. Okay, so the boundary conditions are as follows: at x1 equals 0, y equals 0, which means that 0 is equal to 0 plus c4, which means c4 is equal to 0. At x1 equals 0, the rotation is equal to 0, which will give me that 0 is equal to c3. At x1 equal 5, the shear is equal to 125 kilonewton, which tells me that C1 is equal to 125 kilonewton. At x1 is equal to 5, the moment is equal to 0, which tells me that zero is equal to C1 multiplied by 125 multiplied by x1, which is 5, plus C2, which means that C2 is equal to negative 5 multiplied by 125. When you substitute C1, C2, and C3, you find that your displacement is equal to negative 125 divided by 6EI multiplied by 3L x1 squared minus x1 cubed. How did I find that? All I did was, this is y, C1 is 0, C1 is 125, so I put 125 here, and C2 is negative 5 multiplied by 125, C3 is 0, and C4 is 0. So you end up with this equation. The rotation is equal to negative 125 over 6 multiplied by dy by dx. So EI dy by dx is equal to negative multiplied by 6L x1 minus 3x1 squared. The shear at the moment is equal to negative 125 over 6L minus 6x1. And finally the shear, which is equal EI d3y by dx1 cubed, will be equal to negative 125 multiplied by 6, negative 6 over 6, which is equal to 125. Okay. Now, what we need to do is find the displacement and the stresses across the beam. So the displacement is given by u, which is equal to x minus x. X minus x, which will give you the following. Negative x2. If you look, I'm just going to scroll back to see the displacement of an Euler Bernoulli beam. Here's the displacement of the Euler Bernoulli beam. The horizontal displacement is equal to this, and the vertical displacement is equal to y, and the third displacement is equal to 0. And sigma on 1, the stress at any point in the beam is equal to negative the moment multiplied by x2 over I. So at any point on the beam, the stress at any point sigma on 1 is equal to function of x1 and x2 of the horizontal position and the vertical position. Where is that point horizontally and where is that point vertically? And this function is equal to negative mx2 over I, where the moment is equal to negative 125 over 6 EI, that's the moment, negative 125 over 6 EI multiplied by 6L minus 6x1. So this is the function of x1 multiplied by x2 divided by I. I'm sorry, there's no EI here. The moment is equal to negative 120. The moment is equal to EI d2y by dx1 squared. So the moment is equal to this value, which is the value that I put here. Negative 125 over 6L minus 6x1 multiplied by x2 over I. So this is the value of sigma on 1. The value of sigma 1, 2, which is the value of sigma 2, 1, is equal to minus the shear multiplied by Q divided by IB. B is 0.25 meters. I is equal to 0.25 multiplied by 0.5 cubed divided by 12. It's the moment of let me just put it next to the cross section. This is the cross section. The moment of inertia is equal to 0.25, the width, multiplied by the height cubed over 12. the shear is equal to 125, so negative 125, and the Q is given as the area multiplied by the distance from the neutral axis, and we discussed this when we derived the equations. This is equal to the area, which is the width of the beam, multiplied by the height, which will T over 2 minus x2. So this is the area. Y bar, let's just draw the cross-section area. This is the cross-section. This is the point at which we would like to calculate sigma 1, 2. It's at a height x2. This distance is T over 2. So the height of this area is given by T over 2 minus x2, and the distance of the centroid of the area to the neutral axis is equal to x2 plus half the height, which is 1 over 2 T over 2 minus x2. And so you put Q here, and this gives you sigma 1, 2. So your stress at any point inside the beam is given by a matrix, because the stress, as we know, is a matrix of values, where you have a value of sigma 1, you have a value of sigma 2, you have a value for sigma 2, and non-zero value, and the rest is equal to 0. So these are the numbers. Now let's visualize the results. When you plot the displacement of the beam using a vector plot, and we'll show you this in another tutorial using Mathematica, a vector plot of the displacement, you get that the points here are moving down more than the points here, and indeed, because it's a cantilever beam, so you get the points here move down more than the points here. This is a contour plot of sigma 1, 1. When you draw a contour plot of sigma 1, 1, in KPA, you get the stresses at the top, because remember this is a cantilever beam, the stresses at the top are higher closer to the support, and at the bottom are higher closer to the support, and decrease as you get closer to the load, and the stresses on the neutral axis are 0, and the stresses at the top are positive, and the stresses at the bottom are negative. When you look at the contour plot of sigma 1, 2 in KPA, you find that this shear stress is actually very small. It's higher. The shear stress is 0 at the top, 0 at the bottom, and increases with this shape. And in the middle here, it's around or over about 1400 kPa. When you draw a contour plot of von Mises, you'll find that it does not differentiate. This is very important. It doesn't differentiate between positive sigma 1, 1 and negative sigma 1, 1. So you see at the maximum von Mises is here and here, and at the top it's 50,000 and the bottom is 50,000, and so, and in the middle it's closer to 0, and the stresses here are less than the stresses near the support of the cantilever beam. Now, the next thing we asked for is the principal stresses at different locations at the support, where this is E1, this is E2, this is E3, and I'm wondering what the principal stresses are at the different points on the beam. At this point, I evaluate sigma on 1 and sigma on 2. You will find that the stress will have 60 MPa 0, 0, 0, 0, 0, and 0, 0, 0. And so the principal stresses at this point will be 60, 0, and 0, and the directions will not change, and so the principal stress direction is E1 and the principal second direction is E2. And similarly at the very bottom fiber. In the middle here, at x2 equals 0 and x1 equals 0, the stress matrix will actually have a value of 0 and will have a value for sigma on 2 and sigma on 2, 0, 0. And you will find for this state of stress, the principal directions are oriented at 45 degrees, and you will find values for the principal stresses to be negative 1.5 and 1.5 MPa. And similarly for a point in this location and for a point at this location. And you can evaluate this using Mathematica and or using just by finding the eigenvalues and the eigenvectors of the stress matrix. Now, just to give you a bit of why I would want to do this, so a bit of the application of something like this. Whenever you design a cantilever beam, and let's say I'm going to make it out of concrete, I care for the direction of the principal stresses. So at the top here, the principal stresses are in the tension direction. So I'm pulling the concrete in this direction. Because I'm pulling the concrete in this direction, usually you find that in a cantilever beam, they put steel bars at the top to take this tension. In the bottom, there's more compression, so I don't really put a lot of bars closer to the bottom fiber of that beam. I might put just to make it strong, but I don't really need them to take any kind of any tension. When you look at in the middle of the beam, you'll find that the principal directions of the stresses, you have tension in this direction and compression in the other direction. Tension in this direction, you end up putting some steel bars for shear. Some other people use something called shear studs. So they put shear studs in this direction just to take this type of tension due to the existence of the shear stresses at this location. But the reason why you put those bars is to take the tension, or they're usually aligned with the principal stress directions that are tension. You have different other problems throughout your notes. For example, problem number 6.4.2.c, we already showed how to solve it in the derivation above, and this is a simple beam with the Young's modulus is 20 gigapascal. The beam, it's a simple beam with length that's equal to 8 meters. The boundary conditions are y is 0, moment equals 0, y is 0, moment equals 0. Now there are many other possibilities for beams. So for example, a beam like this, fixed, the boundary conditions would be y equals 0 and the rotation equals 0, y equals 0 and the rotation equals 0. So check those examples in your notebook, in your textbook. So in the next couple of examples, we are going to go through beams in which we are applying horizontal or loads in the direction of the principal, so in the longitudinal direction of the beam rather in the lateral direction of the beam. So instead of applying lateral load, we're going to apply axial load on the beam. So let's start with an example in which we have a beam under axial load and we have displacement boundary conditions on the beam. So we have a beam that's fixed at both ends and is under a triangular axial load. So I have something right here that's pulling this beam towards it. So for example, this could be gravity or could be any other type of load, distributed load that's pulling this beam in this direction. The load is a triangular axial load with a maximum value of 125 kilonewton. Whenever I have a triangular load, I have to find an equation for that load because I'm using a differential equation. I'm solving differential equation, so I'd like to have equations for that distributed load, and the equation is going to be as follows. When x1 is 0, this load is 0, and when x1 is L, the load is 125. So the equation, let's say this Q or P, the distributed load, is equal to 125 in the positive direction multiplied by x1 over L. When x1 is 0, I get 0. When x1 is L, I get 125. So this is the equation for the distributed load. The beam's length, width, and height are 5 meters, so L is 5. And the cross section, if I look at the cross section of the beam, this is 0.25 meters, and the height is equal to 0.5 meters. And Young's modulus, E, is equal to 20 gigapascal. And as usual, ignoring Poisson's ratio. We need to find the displacement and the stress, and we need to draw the contour plot of sigma on 1 and the vector plot of the displacement along the beam. I would like to know where sigma on 1, what the value of sigma on 1 is throughout the whole beam. Now, this is a beam under axial load, and I would like to first find the equation of equilibrium that I need to solve. In order to find the equation of equilibrium, I will take a sliver of the beam and find the forces acting on that sliver of the beam. So this is a sliver of the beam. Its length is delta x1. Right here I have a normal force. The normal force is equal to, or the normal stress is equal to sigma on 1. And right here I have sigma on 1 plus a little bit more. And right here I have an area, and right here I have another area. It's the same area. On here I have a distributed load that's equal to P, which is equal to 125 x1 over L. This is per unit length, so I have to multiply it by delta x1 to find the actual force. Okay, so let's try to solve, let's try to write the equation of equilibrium. The force on the right, sum of forces equals 0. Force on the right is sigma on 1 multiplied by the area, and let's use negative. The force on the left is sigma on 1 plus partial sigma on 1 by partial x1 dx1 multiplied by the area. the distributed normal force is equal to P multiplied by dx1. It's distributed per length, so I'll multiply by length to get the total force. This is equal to 0. You'll find that sigma on 1 will cancel sigma on 1. And you'll be left with the following. Partial sigma on 1 by partial x1 multiplied by the area plus P equal to 0. Now, the next thing is the boundary conditions are given for the problem. So this is my differential equation of equilibrium. But the boundary conditions are given in terms of the displacement. U is 0 and U here is equal to 0. Now, how can I solve such a problem when the displacement is actually giving, when the boundary conditions are given in U, but the differential equation are given in terms of the stress? Well, that's why we have a constitutive law. The constitutive law states that sigma on 1 is equal to E epsilon on 1. So I need to know something about the displacement. So I need to replace sigma on 1 with epsilon on 1. Now what is epsilon on 1? Epsilon on 1, or the strain in general, is half the gradient of U plus the gradient of U transpose. You'll find that epsilon on 1 is the first component in this, and this will be partial U1 by partial x1. So I need to find the horizontal displacement and take a derivative of it with respect to x1. So when I look at the beam, I'm actually going to assume that the displacement is actually made out of only one component, which is u1, and the rest are zeros, and this is in this direction, u1. And u1 changes according to x1. u1 is a function of x1, everything else is 0. And so I'm able to then say, therefore, the stress sigma on 1 is equal to E multiplied by epsilon on 1, which I can replace with du1 by dx1. I'm going to take the sigma on 1 and then put it here, and replace partial with d, because this is the only variable, the only unknown, or the only variable is dx1. Everything is function of dx1. Instead of sigma on 1, I'm going to put E du by dx1 multiplied by the area plus P equals 0. And you get this differential equation of equilibrium that says du1 squared by dx1, du1, this 2u1, the second derivative of u1 with respect to x1 is equal to negative p over ea, where p is equal to negative 125 x1 over lea. Okay, so u1, when I integrate this twice, will be equal to negative 125 x1 cubed over 3 by 2 by LEA plus C1 x1 squared over 2 plus C2. I just differentiated it twice quickly, and it's function of two constants, C1 and C2. I need two boundary conditions to find C1 and C2 using boundary conditions. We can find C1 and C2 at x1 equals 0 their displacement is 0, and at x1 equal L, the displacement is also equal to 0. So U1 is equal to, from this you'll find that C1 or C2 equal to 0, and from here you'll find that C1 will be equal to 125 L over 6. B A. Therefore, I have U1 a function of x1, and epsilon 1 is equal to du1 by dx1. I can get the strain, and I can get the stress using the constitutive law, that the stress is equal to E multiplied by epsilon 1. And if you draw the contour plot of all these things, you end up with this distribution. This is sigma on 1. It's tension at this side and compression at that side. So because of the distribution of the load, it's putting tension on one side and putting compression on the other beam. And when you draw the displacement, because the displacement vector has U1, 0, 0, you'll get that the displacement is higher in the middle, 0 at both ends. And we're going to go through another tutorial in which I show you how to do this in Mathematica. In the next problem, it's exactly the previous problem, but the difference is I have two different boundary conditions. Here the displacement U1 is 0, while here I have a different boundary condition which states I have a free end. I don't know what the displacement is, but it's a free end, which means that the stress at this free end is 0. I've got nothing pulling here. I have a distributed body force of 125 kN. It might be because I'm hanging this from the top here and this is the ground, so I might be pulling. And maybe the weight here is more than here, but so basically I have 125 kN acting on this point. So I expect the stress distribution to be totally different and everything to be totally different just by changing this boundary condition. So everything is the same except the boundary conditions of the problem. By changing the boundary conditions, you end up with a different distribution of the stress, and the maximum stress is actually now here, sigma on 1, maximum in tension, and here the stress sigma on 1 is equal to 0. And the displacement is maximum here and 0 here. Other alternative for the boundary conditions are as follows. So for this particular problem, the boundary conditions are: I have a distributed load and U1 is 0, sigma on 1 is 0. Another one would be P is equal to 0 and the sigma on 1 is equal to force divided by the area. For example, I put a force here, so the boundary condition would be putting sigma on 1 here and U1 is 0. Another boundary condition could be I put P here and I put a force here. Here U1 is 0 and the boundary condition here is sigma is equal to the force divided by the area. Or what else? I could also pull the beam with a known displacement. I could give you that U1 is equal to 5 millimeter, for example. So the boundary condition would be U1 is equal to 5 millimeter, U1 is 0, and maybe given a certain distributed load. So other examples of boundary conditions. Of course, I can switch the supports. I can switch the support with this support. The last example in this chapter is I take that beam and I just put it upside down, and I have the cross section changing, and I hang a force from it, and I also have a weight that's equal to rho multiplied by A. It's the same. I have to make severe assumptions to be able to solve this by hand. And so this the problem states the shown beam has a varying cross-sectional area with a radius of r equal to 2 units and r equal 1 unit at the bottom. And as you can see, the radius varies linearly. So let's try to find r as a function of x, and I call this x1. I know that r is equal to 2 when x1 is 0. So it has to be 2 minus a number. And this number is equal to, when x1 is 0, is equal to 0. So it's function of x1. And is equal to 1 when x1 is equal to 4. So I should divide this by L. Now I did this quickly because I know the answer, but usually in general you have to think about it. And so indeed, that's in meters. At x1 equals 0, r equal 2 meters. At x1 equal L, r is equal to 2 minus L over L is equal to 1 meter. Okay, so I found the radius. I also need to find the area, because here the area is a function of x. So the area is equal to pi multiplied by r squared. Okay, so this is the cross-section area. Now I need to write my differential equation of equilibrium to solve it. The differential equation of equilibrium will look like this. Here I have sigma on 1, and I have an area. Here I have sigma on 1 plus partial sigma on 1 by partial x1 dx1. And the area is not the same area. I'm going to call this A, the area at distance x1. This is the area at the distance x1 plus how much the area changes with respect to x1 multiplied by dx1. Because the area changes, the cross-sectional area varies. And I have rho multiplied by the area as a distributed load, which has to be multiplied by dx1 to give me the total force. So the sum of forces in the x1 direction equal to 0, negative sigma on 1a plus the force or the stress multiplied by the area is equal to or plus as well the distributed force multiplied by dx1 equal to 0. Sigma on 1a negative plus sigma on 1a plus sigma on 1 partial a by partial x1 dx1 plus partial sigma on 1 by partial x1 a dx1 plus something multiplied by dx1 squared plus rho a dx1 equals 0. This will cancel this. dx1 will cancel dx1, will cancel dx1, will cancel the 2, and I can actually remove this because this is very small compared to the other terms because it has 2 of them, dx1 squared. So I'm going to be left with sigma on 1 partial a by partial x1 plus partial sigma on 1 by partial x1 a plus rho a is equal to 0. And this is the differential equation of equilibrium that I'm trying to solve. And I can replace the area as pi 2 minus x1 over L squared, and dA I replace partial a by partial x1 with dA with respect to dx1, which is equal to 2 pi 2 minus x1 over L multiplied by negative 1 over L. And so I'm left now with the equation, what is sigma on 1? My unknown is sigma on 1. And this is the differential equation of equilibrium. And I could replace sigma on 1 with epsilon on 1, which is E partial u1 or du1 by dx1. I could put this here, and then the differential equation is in terms of u1, and it has the following boundary conditions. At u1 equals 0, the displacement is 0. And at u1 equal L, let's look at the beam. Sorry, at x1 equal L. Right here I have a value of P, which means I know the stress at this point. Sorry, at x1. So the boundary condition is at x1 equals 0. At the top of the beam, the vertical displacement is 0, and at the bottom of the beam, the stress, which is E multiplied by epsilon on 1, which is E multiplied by du1 by dx1, is in fact equal to divided by the area, which is P divided by pi, and the area here is equal to r squared, pi r squared, and r is equal to 1 meter. And this differential equation is slightly complicated to solve by hand, and so if I give you a problem like this in the exam, I will ask you whether this is the correct differential equation of equilibrium or not, and in the next tutorial I will show you how to solve these things by hand. So as a final note for this chapter, what we are doing here is that we are solving beams using very severe restrictions on the displacements of this beam. We are assuming that the only allowed displacement is that the plane sections remain plane after deformation and remain perpendicular to the neutral axis of the beam. Now, in general, if you're more interested in stress concentrations at certain locations in beams, you need to do a more detailed analysis and solve the equilibrium equation in terms of all the possible stresses: sigma 1, sigma 2, sigma 2, sigma 3, and so on. And in this case, you need to utilize the constitutive law that relates all these stresses with all the strains, and you need to find the stresses and the strains at every point without any restrictive assumptions. And for this, you need to use finite element analysis, and that's why you end up with, nice, colorful pictures that shows you the stresses at every point in a more accurate manner without those restrictive assumptions that we're using. And in these cases, you will find you can draw, for example, using finite element analysis, as you see here, a map that shows you the direction of the principal stresses at every point. So, for example, closer to the support, you'll find that the stresses are higher in this direction. Closer to the middle of the beam, the principal stresses have this direction. And so based on this analysis, you can, if you're using concrete, for example, you'll be able to align your steel bars according to the direction of the principal stresses. You'll find for this particular simple beam, you don't have any tensile stresses at the top, so you would minimize the number of steel bars that you use in the top. And so this is it for chapter 6. We presented the beam as a special example of the continuum mechanics problem that we introduced in the previous chapters.